All right. Hello, everyone. Welcome back to Comp 3430 Operating Systems. I hope that you are all keeping warm today. I hope you're all keeping warm today. It is just like whiplash in terms of the way that this weather is moving around. And yeah, I hope you're all keeping warm today. It is Friday. It is Friday. It is a good day. Fridays are always good days. Yeah, I hope you're doing good today. Let's get started. So this week we're kind of sort of continuing talking about file systems, but it's really a lot more from the perspective of like, how do I make sure that the data that I'm writing to my disk stays consistent, and how can I make sure that I have, in terms of RAID, some kind of hardware support for things like reliability and increasing the capacity of the drives that I've got. Today, what I want to focus on is file system checking as a concept, and I want to spend some time taking a look at some code that I've prepared. It's not complete, but it's kind of intentionally not complete because it's the kind of code that would be a little painful to spend a lot of time working with. I want to take a look at some code that does some basic file system checking with ext2. And then what I want to do is I want to spend some time taking a look at some Linux kernel source code for the ext4 file system. I guess I want to make sure that I'm clear immediately that whenever we're looking at Linux kernel source code in this class, it's for fun. It is for fun, yeah. Mainly my goal with showing some Linux kernel source code is to show you that it is actually just C code. It's just C code. Somebody wrote this, it's code. It's a program that somebody wrote. The purpose of today's lecture, in terms of taking a look at this source code, is let's see where journaling actually happens in this file system. So like, what are the stages of journaling? How are they written in this file system's code? But like, I'm never actually going to ask you questions about the Linux kernel unless like I pointedly point at my nose and say this is something I'm going to ask you about. But for today's lecture, for sure, it's more of a let's just take a look at this code and see that it is C code that was written by a real person. And this is what journaling actually looks like from a code perspective. So what I want you to be able to do by the end of today's lecture is identify inconsistencies in a file system. We're going to take a look at some code for ext2, and we're going to take a look at how we might structure this code and what kinds of things we could be testing for when we're trying to identify inconsistencies in a file system. And then I want you to be able to at least make some sane decisions about how to repair an inconsistency in a file system. So in the code that I've prepared for us today, I've written in some questions. So like, what data structures would be, what data structures could we refer to try and find consistency between the data structures that we've got right now? And so this then is also going to be pretty closely related to this learning outcome that keeps showing up. Show how common file operations are performed in terms of manipulating a file system's data structures. So which data structures in this case are being updated when a file is being updated, and which data structures then can we refer to try and find or identify inconsistencies, and then find out what we can get to be the correct value of the thing that we're supposed to be looking at right now. Again, notice that Linux kernel source code stuff is not here. That's not something I want you to be able to do. I want you to be able to see it, but I'm never going to assess you on that in terms of what we're looking at for today's lecture. So it's Friday today, so what I want to do first is I want to take a look at what we're going to be doing next week and take a look at some of the chapters that I'm asking you to read for next week. So I'm going to go to the course schedule for today, and the topics for week 5 are posted up here. Next week, we're going to be starting to look at concurrency in operating systems. And the way that we're going to look at this next week is with this really coarse-grained concurrency mechanism that's called processes. And the really short of this, we're going to spend all of next week doing this, but the really, really short of this is when you run a program, it becomes a process. That's what we're thinking about here. We're going to be looking at how we, as programmers writing C code, can ask the operating system to create new processes, and how we can ask the operating system to help us manage processes from a mechanical, like, these are the functions that I need to call, these are their side effects, and these are the kinds of things that we can observe as this is happening. I want you to be able to describe the life cycle of a process. So we're going to be talking a little bit about how a process can move through different states. We actually did see this already a little bit, but I want to look at it again in a context that's more closely related to processes. I want you to be able to do things like describe and distinguish context switching and mode switching. So this is described in chapter 6, and this would also be described in the video if you choose to watch that. We're going to spend time determining what an operating system might need to know about a process, and then describe how an operating system manages processes. So really kind of general high-level stuff about how the operating system is actually going to do this stuff and enable all of this stuff for us. There are 3 chapters for next week, but I'm going to pick on this chapter specifically. This is chapter 5 that I'm asking you to read. This chapter is the process API. And in the same sort of sense that we had a chapter that was about the file system API, so like how to do read and write and stuff like that, this chapter is really here as a reference more than anything else. This is describing the functions that you're going to be using to create and manage processes on a system. I'm not expecting you to memorize this stuff. Like, going through this chapter fairly quickly to just get a sense of what these functions are is enough for what we're doing with this chapter. We're going to be spending lots of time looking at these function calls in class, writing code that uses these function calls, and I'm not going to expect you to do things like memorize what the arguments are for these things. You should have a sense of what their side effects are, but we'll see that in class in addition to in the chapter itself. The other 2 chapters that are here are kind of the ones that are important in terms of, like, there's stuff in here that I want you to be able to get. But chapter 5, I'd almost go as far as to mark it as an optional reading as opposed to a required reading because we're going to see this so much in class. I'm excited to look at this topic because, file systems I think is really cool. This is actually one of my favorite topics of operating systems, file systems. But file systems, in terms of like the difference between what we've done before and what we're going to be doing is limited, actually. Like, it seems like it's quite different because we're looking at low-level bytes and hex and stuff like that with the values that we're looking at, but it's really early data structures. We're looking at like lists and trees and really not much more than that in terms of the actual stuff that we're doing. Processes is kind of a mind-blowing thing where we're actually going to have like stuff happening literally at the same time, and that changes a lot of the stuff that we're thinking about and how we're thinking about it. All right, so what I want to do now is spend a little bit of time taking a look at inconsistent file systems. I want to remind you first of this definition of what an inconsistency in a file system is, and that is that we have different properties in our file system, in the metadata for our file system, that don't agree with each other. So we've looked at 2 different file systems in extensive detail at this point. We've looked at ext2 a lot, and we've looked at exfat a lot. And one of the things that we have seen in many of these different data structures is that they have different values that refer to the same things. So for example, we might have an allocation structure, a data bitmap. We have this concept in both exfat and ext2. We have this allocation structure that marks blocks as used or unused. But we also have inodes in ext2. And inodes themselves have direct block pointers, and the direct block pointers that they have indicate pretty clearly that that block is used. These are two different data structures that are both referring to the same kind of part of our file system. When these things disagree, when we have inodes that refer to data blocks that are marked as unused in the allocation bitmap, we have an inconsistency in our file system. We have two different data structures that disagree about the state of something. When we were doing all of those examples last class of like, these are the different situations that can happen, there was one that I wanted to call up again in terms of identifying whether or not this is or is not an inconsistent file system. So the situation that we were in last time was that I have this picture of my cat, and I'm making this cat picture bigger to put a picture of myself into it, and our system is crashing at some point in the middle of doing modifications to the file system's data structures and the data that we've got. So we're going to say here that the situation is that with VSFS and ext2, we've updated the data bitmap. We've updated the inode, so we've changed the file size and the direct pointers, but we haven't written the data block yet. So I've made changes to the data structures in my file system, but I haven't actually put the data on the disk. I haven't taken that picture of me, a stick figure, and actually laid those bytes down in my data region. If we're thinking about exFAT, we're going to say that we've updated the data bitmap. So we went to the root directory, we found that data bitmap directory, the directory entry for the data bitmap. We've looked at the cluster heap. We changed the data bitmap in the cluster heap. We updated the stream extension for the file. So we've indicated that it does have a little bit bigger of a file size. We updated the FAT. So we put a new cluster in the cluster chain, but we haven't actually written the cluster. So we didn't write the data to the actual disk. There is no block or cluster that has that picture of me in it. When I open it up in Paint, I'm going to see that old picture plus like a bunch of garbage because I never actually wrote those disks. I never wrote that block or that cluster to the disk. I also am able to see that the file size is bigger because I've updated the stream extension and I've updated the inode, and there appears to be less available space on the disk because I updated the allocation structures for this thing. My question for you is this file system consistent? Take a second to think about this, and this is very much just a thumbs up, thumbs down, and I'll give you a count of 5 or something. I'm looking for thumbs up, yes, this is a consistent file system, or no, this is not a consistent file system. We were interrupted. We did not actually finish writing everything that we were supposed to write to the disk. But is the file system itself consistent? So I'm gonna look at the board here for a second. I'll count to 5, and then I'll turn around, and then I want to see thumbs up, thumbs down, okay? So 1, 2, 3, 4, 5, thumbs up, thumbs down. I see about 7 thumbs up. Okay, so awesome. 7 people think that this is a consistent file system. Yeah, absolutely this is a consistent file system. We didn't finish writing everything. The data was never actually written to the disk. But in terms of file system consistency, the data is irrelevant. The data is not actually important. File system consistency is 100% about the data structures in our file system and the consistency that those data structures have with each other. So in this case, the data bitmap is consistent with the direct block pointers that we have in ext2's inode. They both agree that these blocks are used. They don't care what the data is, but the blocks are used in this thing. With exFAT, the data bitmap, the FAT, and the stream extension all agree that that new cluster has been occupied by something. But the data isn't there, and that's not actually important for the data structures in the file system itself. All right, does that make sense to everybody? Okay, awesome. So what I want to do next is I want to spend some time taking a look at file system checking. And what I really want to do is spend some time taking a look at code that is going to be responsible for checking an ext2 file system. The big idea with file system checking is very much like, something bad might happen. I don't know. I'm just going to keep using this file system and let it crash. And then once it crashes, and then it coming back up again, I'm going to check to see if all of these data structures are consistent with one another. Once I get to that point of checking to see if these data structures are all consistent with each other, then I can try to repair the file system if I find an inconsistency with these things. So we're going to start here. I've put these links up on the course web page under today's lecture, so you don't have to come to the slides here to find this. But this is the GitHub repository for a suite of programs that are called E2FS progs. This is all of the code that is responsible for doing things like file system checking for ext2, ext3, and ext4 file systems, among other things. I'm specifically wanting to look at the code for E2FSCK, E2FISC, so that's this directory right here. This is all of the code that has been written to check ext file systems when they come back up again. I'm going to click on super.c here, and what I'm going to do is scroll down a little bit, and scroll down a little bit, and scroll down a little bit, and then kind of immediately say that, wow, this is complicated. Wow, there's a lot of stuff in this. There's a ton of stuff in this. And part of the problem with this code is that this code has been written to check file systems that are all of ext2, ext3, and ext4. And there have been a lot of changes to this file systems, like this family of file systems over the years. A lot of this code is very much just like, I'm going to find regions and I'm going to check values. There's stuff in here that is kind of cool to look at, like this idea of processing an orphan file. So an orphan file is going to be a file that has an inode, but it's not in a directory structure anywhere. It doesn't actually appear in a directory. There's an inode for it in the inode table, but it doesn't appear in any of the directories that we have in this system. So the idea here, a correction that you could make to this is, it is a file. I can find it in the inode table. I can't see that it's in any of the directories that I've got, so I'm going to put it in a directory. If you remember when we were looking at ext2 in the first place with hex dump, we found a directory that was called lost plus found. This is the directory where we would take these orphaned files and just stick them in there. I found this file. It's got to go somewhere. I don't know where it should go, but this is a sane place to put it. So if I check something and I find that this file is orphaned, I can put it in this directory and tell the operator, look, you need to look in this directory to find this file. Yeah?
How would that, how would a file become orphaned like that? Like what point would it crash to make it like that?
So that's a good question. At what point could our file system crash to have a file be orphaned? And something like this could happen when you are in the process of moving a file from one directory to another, where you are going to have to delete a directory entry in one and then create a new directory in another. If you crash in the middle of, I've deleted it, but I haven't added it to the other one, then that's a possible situation where this could happen. In theory, I suppose it would make more sense to just do it the other way around, create the new directory entry and then delete the old one as part of that operation. But that's an example of where something like this could happen. Yeah. Any other questions about that? Okay. So yeah, this is too complicated. I don't actually want to step through this code because there's just so much that's going on here. Instead, what I want to do is I want to take a look at some simpler code. If you want to follow along with what I'm doing, my plan here is that I'm going to basically debug this code. I'm going to run this code through a debugger and step through it and take a look at it this way, as opposed to just reading code aloud at you. If you want to follow along with what I'm doing, and you have this ext2 inspect code on your system already, you can just pull the changes that I've made to this repository to your local copy of it, or to whatever you have on Aviary. Or if you don't have this repository already, you can clone it. And I've linked to this repository in the course notes for today, but it's the same repository that we were looking at before. So I'm going to head over to my terminal here. And I'm currently in this ext2 inspect at the back. Is this okay for you? Yeah, okay. I'm in this directory, and I'm gonna pull this code. So I've made changes to this repository, and I've pushed those changes to the repository, but I don't have them here, so I'm gonna do git pull. Git pull is gonna pull the changes that were made to the repository into this directory that I've got here. So now that I've done git pull, I have added 2 files to this repository that are important for us to take a look at. There's ext2 fsck, ext2 fisc. We're going to take a look at that. And I've also added a new file here that is ext2 volume inconsistent bitmap. I've taken the file that was in this directory before that's called ext2 volume, and I've opened this in a hex editor, and I've manually manipulated the data bitmap. So I've made the bitmap inconsistent with other things that are in our file system's superblock description for the purpose of like showing this is what an inconsistent file system might look like. So I'm going to pop open ext2 fsck here. And I do want to spend just a little bit of time taking a look at some of the code that I've got. I'm going to show you starting down here at line 26 and below, I guess. I didn't type all these data structures out to be really, really clear. I just copied them from Linux kernel source code. I didn't spend the time to actually type any of these data structures out. I just stole them from the Linux kernel, but the Linux kernel defines all these types, LE32, for example. This represents little endian 32 bits. We're on x86 for the most part. We're on x86 systems, and so that is a little endian system. And so what I've done here is just redefine those types as unsigned integer types that have the same number of bits. But we've got a superblock structure. We've got an inode structure here. We've got a group descriptor. So this is that thing that has our inode table and inode bitmap references. And then I've got a directory entry here. After this, this is the code that I've actually started to write myself for the class today. So what I'm going to do is I'm going to actually close this for now. And I'm going to make the code. And I'm going to run it directly through my debugger. So I'm going to be using LLDB to take a look at this. I'm going to break on main, and I'm going to run it. Oh, this is something that I think is cool that's changed in the last couple of years since I've been using LLDB. It used to be that you couldn't pass arguments to your program with LLDB like this. It would just not do it. It just kind of like freak out and not really be happy with what you're asking it to do. And you'd have to basically do this part manually, and now it's smart enough to figure it out. So I'm delighted that it's able to figure that out, and we can just pass these values on the command line. All right, so I'm going to step through this code. We have some initial values that I'm setting up, and kind of like with the other things that I've done, I'm creating instances of these structures, and I'm initializing them all to 0. I want to make sure that there is nothing in them before I start, because when I'm loading values into them, I don't want to have read maybe not enough and just happen to get garbage values in there that I'm not expecting to be in there. To be clear, read should overwrite everything with what was in the file in the first place, but this is me just like safety checking and making sure that I don't mess myself up when I'm doing something later. So I've got an instance of the superblock struct, I've got an instance of this group struct, I've got an instance of the root directory, and I've got an instance of a directory entry so that I can work with all of these. I've got some extra values that are going to make a little bit more sense once we get to taking a look at our file system itself. But we're going to step into opening the file system. And then if we're thinking about ext2 again, remember that our superblock starts at byte 1024. It always starts 1 kilobyte into the file. So the first thing I'm going to do here is seek to that location in the file. Once I've got that, I'm going to read the superblock itself. So I'm going to read the superblock into my superblock structure. And at this point, I can take a look at what's in the superblock, which is a lot of stuff. But up at the top here, we've got stuff like inodes count, blocks count. And if you remember, these were the values that we were getting out when we were reading this with the simple version of the superblock struct that I gave to you before. We're going to keep on going with this. And so I'm going to hit N on my keyboard. And the first thing that we're testing here is that magic value. So ext2 magic is defined as this EF53 value. So P/X tells this to print in hex format. This is just checking to see if that byte that, or that 2 bytes that we're able to read in our superblock are actually consistent with what we were expecting them to be. So this is actually an ext2 file system. So I'm going to hit next. Then what I want to do is I want to figure out what the block size is for this file system. The block size is going to be something that gets configured when we created the file system in the first place. The block size value that we have in the superblock is kind of like that whole bytes per sector shift value that we're doing with exfat. But with ext2, we're using 1024 as the base for the thing that we're raising this to. So we're going to be using this, this shift operation, and this expression is defined in this document that, that we were taking a look at. But if I hit N and I inspect block size here, then what I should get back is 4096. I'm going to actually open up this document in my web browser. And what I want to see here is this is the block size, and it's this log block size because we're using powers of 2 to get the actual value. But what we have here in the description is this value may only be non-negative, and then common block sizes include 1, 2, 4, and 8. Think about this for just a second. What would we validate about this value? What could we validate about this value if we were actually inspecting it and checking the value is an appropriate value? Just think about this for a second. The answer is not much. Like, it's a non-negative number. And if we're putting this into an unsigned value, it's non-negative. It might be really, really big. It might be really, really, really big. But as far as this documentation is concerned, there's not really very much that we can check about this, other than on really old versions of the kernel, it can't be larger than this thing that's called the memory page of the architecture. So depending on the actual machine that we're running on, it kind of defines what the value is. Let's keep stepping through here. Once we have that block size, then we're able to go to where that first block group descriptor is. And this is going to be in the first block after the super block. The code that I've got and I've published for you here assumes that the block size is greater than or equal to 2 kilobytes. And so we should be doing something slightly different if it's smaller, but we're just going to ignore that for now. And so I'm going to skip over this else seek, and I'm going to pass that read. And then what I want to take a look at is the group itself. The group is telling us things like, where is the inode bitmap? Where's the block bitmap? Where is the inode table? How many free blocks are there? How many free inodes are there? How many used directories are there? Here is one of the first places where we can begin to check consistency between structures in our file system. The super block, way up here, has free blocks count. it has inodes count, it has blocks count, it has inodes, free inodes count. Our group descriptor has the same properties. It's able to tell us things like there are this many free blocks in this block group. There are this many free inodes in this block group. These are two data structures that we could be using to check consistency for, to make sure that they are consistent with one another. I'm going to go back to where I was here, and what I'm going to start doing is I want to begin to read through our block bitmap itself, and then counting the bits that are set in there to see if that is consistent then with the other two places where we have the number of free blocks. So I'm going to show this on the left side because I think it's a little bit easier to see what we're looking at here, and then we'll step through this in just a moment. So on line 232 here, we're calculating that block size. And then on lines 238 and 239, we're reading that group descriptor, the block group descriptor. Once we've got this read, we know which block the bitmap is in by looking at this property of that descriptor group. So we can seek to that location. And then what we're able to do here is begin to read bits from our block. Once we have seeked to the block that has the bitmap, and this is that location where, if you remember, we were in hex dump and we went to that location and it was like FF, 0F, and then a bunch of zeros that represented all the bits that were unset, all the blocks that were currently unused. This loop goes through that block that we've got, reads it in 8 bits at a time, and uses something called pop count. Pop count just counts the number of ones that are in each of these numbers. This is an instruction if you have not got Windows 11 on your machine right now, and Microsoft is insisting that you put Windows 11 on your machine, but they say, no, you can't because your machine doesn't support it. This is one of the instructions that it's saying that your machine doesn't actually support. But it's a handy instruction to count the number of bits that are set. The number of bits that are set, this is exciting stuff, I know. The number of bits that are set in that data structure. So we're counting the number of bits there, and then we're determining here in this conditional statement, are the number of bits set? Are the number, oh my gosh, I'm really sorry. Are the number of bits set going to be the same as the free blocks count? So if I take this set bits and I take the total number of blocks in my super block, is it the same as the number of free blocks that are there? So I'm taking a look now at multiple different data structures that have the same information to try and confirm that they all agree with each other in this file system check. So I'm going to go back to my debugger here, and I'm going to step through this. And what we're doing right now is slowly stepping through the allocation structure that we've got, and we're just counting up the number of bits that are set. So I think that the total number here is going to pretty much be 12, because everything else after this is going to be zeros. All the rest of the data blocks in this region are unset. And so once we get to the end of this, we're going to then be able to check to see if it is consistent with the other data structure that we've got, and confirm that it is. After that, what we're doing is we're going to now go to the inode table, and we're going to try and find the directory entries for the root directory in this thing, because what I want to start doing is checking to see if all the files that are stated as inodes in my inode table are actually in a directory somewhere. So the first part here on line 282 is I need to go to the inode table itself, and this was in my block group descriptor. Then we're going to seek to the inode that we want to look at. Remember that the root directory inode has this well-defined location, and it's number 2. And then our inode table is a 1-based array, so we have to reduce the number that we're looking at by 1 because the 0th entry is inode number 1. Once we've got that, then we can start to read in the root directory's inode structure. And once we have the root directory's inode structure, we're then able to go through the block pointers that this inode has, the direct block pointers that this has. And this is referring to the directory entries that we've got for this. This code here is basically going through the directory entries because they're of variable size. Remember that they're not all equal to each other in terms of their length. The actual name is embedded in this thing as opposed to in the directory, in multiple directory entries like it is in exFAT. So we have to keep track of where we are in the block right now so that we're not going to go past the end of a block. The idea here is that we should be going through each inode in this directory entry, each directory entry in this directory, and recording all of the inode numbers that are in this thing. Put them into a set, and then this is going to be all of the reachable inodes that we have in this directory. Once we've got that set, we can go back to the inode bitmap and use the inode bitmap to say, these are all the actual inodes. I want to make sure that all of these are in the sets that I've got here to determine which ones are reachable and which ones are not reachable. So really quickly here, I'm going to step through my directory entries. And so we're going to step to the inode table itself. We're going to read the inode for the root directory. So this is my root directory inode structure here. It's got this value of blocks here, 8. This is the number of 512 byte blocks. I don't know why it's different than the actual block size, but I put a link here to the documentation describing how to use this value. Then iBlock itself is going to be, these are the direct block pointers for this thing. So we'll keep taking a look here at scanning through this. And what we're going to start doing is go to the specific block for the block pointer, the first direct block pointer, and we're going to begin reading these directory entries. So I've read the first part of a directory entry here, and I've read that this is going to be referring to inode number 2, the record length is 12, the name length is whatever this value is, and then I have to read the name separately. So at this point, I've read the complete directory entry. This is that directory entry for that dot. This is the current directory. This is that self-reference part of the directory entries that we've got. And if I keep going through this, I'm going to keep getting more directory entries. And like I said, the idea here is that for each of these directory entries, we would record the inode number that we are getting out of this. So we're going to put 2 into our set a couple of times, but it's a set that we're going to be using to do this. So we'll have 2 in the set. And then we will eventually get to the lost and found directory. That's this one right here. And then the last thing that we're going to see in this is going to be the README file that we put into this file system when we started. So once we've stepped through all the directory entries in our root directory, we will have put all these inodes into a set. And then we're going to go through the inode table itself to find out if all those inodes are reachable. We're not going to do that. We're going to stop right here. We're going to stop right here. Here are some questions that I want to point at so that you can start to think about these things. The first one is, if the allocation structure that we've got here is inconsistent, what are some of the other data structures that we could use to determine what the correct value is? We're going to have free blocks in the superblock, the total number of blocks in the superblock. We're going to have free blocks represented in our data bitmap. And then we're going to be able to figure out from some other structures here which of the blocks are actually used or are unused. So here's the first question I want you to think about. The other question that I want us to think about is down here. If this magic value is not what we were expecting it to be, what would be an appropriate action to do here other than bail out and say that I don't know what this is in terms of repairing the file system that we've got? Just take a moment to think about that. For me, the correct answer is change it to the magic value and then try again. That's the best we can do in this case. There's not much that we can do in terms of checking this magic value. In terms of our data bitmap, trying to figure out which of those values is actually the correct value. This is the part where we then step into inodes and actually check what are all the direct block pointers that are in the inodes that we've got. All right, so this code is up on the course webpage. It's up on the repository for you to check out. You're welcome to use this and to kind of keep building on this if you want to. What I do want to do very quickly here is take a look just at one function in our Linux kernel. This is a direct link to the source code that we're going to be taking a look at. This web page I think is really great. I really like this because it gives us the ability to pretty quickly kind of maneuver around the file system. And so what I do want to take a look at is this is all the code for the ext4 file system. We're going to take a look at this file that's called file.c, and I'm going to go down to line 308. And on line 308, what we've got here is handling inode extensions. But the really important parts that I want to like I said, I'm just hand-waving at this right now. Before we do anything, we start a journal entry. We make this journal entry begin. Then we actually do the update, and then at the end, we stop the journal entry. We do this as 3 steps. Start the journal entry, make the changes, stop the journal entry, and then allow that journal entry to be replayed. End of conversation for the Linux kernel right now. All I want to be able to see is there is a C function that looks like this. It actually does this stuff with journal entries and stuff. All right. I have promised that in the Friday classes of this week and next week, I will leave time for questions. So I am leaving time for questions. I have some pre-prepared questions that have been asked to me already that I will share answers about with you, but I do want to give you a chance to ask questions of me right now. Yeah.
In the NTP FS type enum, there's the expat and then there's the types values. What's the purpose of the types one?
Okay. So I'm gonna bring up the, not this one. I'm gonna bring up this code just to make sure that we're talking about the same thing. Is it here? Yeah. Right here. So the enum here, this part here is just trying to take advantage of this idea that that one is going to tell me how many different possible values there are in this enum, because it's always going to have the biggest value in an enum.
Okay,
so
we need to kind of be prepared for accepting more than just the expats for expat values?
You don't, no. The only thing that you can check or that you should check is that it is equal to this value. Yeah. In later terms, I might change the file system. I might be asking students to do ext2, and then I would change this to be, there are multiple entries in here. And then if I were to insert that, I would be inserting ext2 into, in between exfat and then the types. And then types would increase by 1, exfat would stay the same, and then I'd have another value for this new one. Yeah. How is the assignment going in general? Is it going at all? That's okay. That's super okay. I've come prepared with questions. So here's the first question. What's the deal with this? And actually, that's actually right above what we were looking at, so that's awfully convenient here. What's the deal with this? Number defined max open files. This is the size of your open file table. This is the size of your open file table. This is as many entries as you should be able to support in an open file table when you get to the point of supporting multiple files. I'm going to tell you some things about this that you can make assumptions about. in any code that I'm going to be running against your code, I'm never going to try to reuse file descriptors. So if I call open, and then open, and then open, and then open, and then open, if I call it 8 times, and then I call close, I'm not going to call open again. I'm not going to like force you to try and find an empty entry in here. That's not what I'm going to do with your code. In practice, yeah, you 100% actually would want to do stuff like that, you know, keep track of which entries are currently used and then find the one that is unused to satisfy an open request. But I promise that I will not do that. I'm not going to do that. So you can assume that at most I will call open 8 times, and I will never call it any more times than that in any one program. The other question that I've come pre-prepared with is using open and read. So when you are writing code for this, we have functions here that are NQP mount, NQP unmount, NQP open, NQP close, and NQP read. In NQP mount, your code is going to have to call open. You're going to actually have to make that function call to open the file name that you're given here. So you're going to actually have to ask our operating system at a lower level to open this file for us so we can start working with it. In NQP mount, you're also going to have to call read so that you can read the main boot sector and then start checking those values that you're supposed to be checking as you're mounting the file system. So NQP mount is going to call both open and read on the file descriptor that you get back from open. NQP unmount is going to call close. That's the only thing that it should do, and it's going to be closing the file system's file descriptor that you got back from mount when you opened the file in the first place. Because mount has to be called before you're doing anything else, so you're not passing anything about a file system to NQP open, the mount function should probably also do something like set a file scope variable that has your file descriptor in it for the file system that you're working with. For NQP open, this is only going to call read, and it's going to call read on that file system's file descriptor that you got back. You don't have to reopen anything at that point. You should just be able to work with the file descriptor that's been set. Close shouldn't actually call anything. It should just check to see if this is a valid file descriptor in your own open file table, and then remove it as appropriate so that other calls to things like read are not going to work correctly. The NQP read function will have to call read on the file system volume that you've got. You're going to have to do things like trying to find the clusters for the data that you're working with right now, and then you're going to have to read those values into the buffer that's been passed to you. Get dents, NQP get dents here is also going to have to call read to be able to start manipulating, to try and find the directory entries for that directory that you're trying to get the entries for. When I'm working with this, I guess to be clear, I'm always going to be passing that type of structure that's defined above, this NQP dirent. And whenever I work with this, I'm only ever going to pass one here. The directory entry here that I'm expecting to get back, though, is going to consist of ultimately an entire entry set from exFAT. So it's going to have things like the file size and the name of the file entirely within this structure. So when I call this with one directory entry, I'm going to get back from this the whole thing that I need to represent that file in that directory. All right. Are there any other questions about the assignment? All right. If that's the case, then what I'm going to do is I'm going to summarize here. At this point, you should begin to be able to identify inconsistencies in a file system. In the same way when we were talking about hexdump, I'm not printing out giant blobs of hex on a test and giving them to you. I'm not going to print out giant blobs of text on a test and give them to you for identifying an inconsistent file system. You should be able to identify, given some data structures, these must agree. They must agree. And if they don't agree, then this is an inconsistent file system. You should be able to at least come up with some coherent explanation for how to repair a file system. And so the summary of this part is really very much with specific reference to the number of free blocks. The super block says this, the allocation bitmap says this. I'm going to go find some third reference to this value and calculate what that value is and determine which of these things is actually correct. So begin to step through other data structures like inodes to determine which is the correct value and then set that value correctly in the other thing that we've got. That's it for today. I hope that you all have a great weekend. Stay warm, and I will see you all on Monday. Bye, everyone.